this session, and then the next one, actually, Brendan is going to moderate, so we'll still enjoy some of his insights and ideas.
Okay. Sorry, let me just do this before I forget. There we go. Okay. I'm gonna need a sip of water. Okay, so our next session, which is the final session of the Tile Day, um, is entitled Understanding Ridership Trends, Customer Experience, and Capital Cost Drivers. And we've got four presentations, and I've shortened the bios a little bit to make sure they're all the same length. But the first speaker is Jiao Wang, who was on this morning, but for those who weren't there this morning, he's a PhD candidate at the University of Toronto. He holds a background in computer science, having completed both his MS and bachelor's degrees in the field. His research focuses on enhancing transit management systems using cutting-edge methods in deep learning, reinforcement learning, and large language models. And that, in particular, that last one is what he's going to talk about, Transit Pulse, deriving social media insights on rider experience using large language models. Jiao, it's yours. Why don't you take the screen?
Thank you, Brandon. Let me just share the slides. Can you see my screen here?
Yep.
Great. Okay, yeah, thank you. And really nice to meet you again. And so for this time slot, I'll talk about the transit path, which is a new way of extracting customer feedback from social media using the large language model. So we all know that is quite important for the transit agency to listen to the transit customer to understand what aspect we do right and what aspect we do wrong. And we want to know when do the customer experience some issues or maybe some positive aspect. And for sometimes we also want to know where do the customer encounter this experience. So in the previous, we do this, we collect the customer feedback through physical online service. So while the services are quite effective, they have a limited reach and can be quite costly. And this process requires significant investment in terms of money, time, and labor. And moreover, the feedback sections through the service tend to be delayed and often happening on a yearly basis. But on the other hand, using the social media can give you some new idea. Like using the social media, you can reach to a bored customer and also you get crowdsourced information. And this process could be more cost effective. And more importantly, compared to the physical and online service, it can give you a relatively real-time feedback. And also because of the massive data set you collected from the social media, it is capable for you to do a furthermore data analysis using more complicated data analysis tools. But still, things is not that perfect. There are still a lot of challenges using the social media data. The first aspect of the challenge comes from the data source itself. Because of the data quality, we all know that the tweet data is relatively low quality data compared to the social media data, compared to the service data. And also it will contain complex linguistic structures such as sarcasm or the irony stuff. And also for the social media data, it lacks of actionable information because it is less constructed and less specification compared with the service information, service data we collected. And also because of the large volume of data, it's hard for us to manage those many data, and also it's hard for us to give a really efficient and effective way for processing all those data sets. And this leads to the second part of challenge, which is related to the tool we use for extracting information from the social media. This diagram is actually a previous TEL project to extract sentiment information from social media. As you can see, you have to go through a really complicated pre-processing. A lot of works has to be done either by human labor or like continuously a lot of iterations of the process. And the limitation is also coming from the vocabulary side because the traditional like NLP method, the natural language processing method, is rely on fixed lexeme, and it's also lacks of a textual understanding. For example, it lacks of the ability to understand the sarcasm and irony inside of the tweets, and also it lacks of the domain-specific information, and it struggle with the word ambiguity in the tweets, and it also has a limited analysis scope, and it's also lack of adaptability. And I want to give you a quick look at this example. So this word cloud is generated based on the tweets related to Bloor Station collected at 9 a.m. to 10 a.m. So as we can see, the largest word here is Bloor, and Lion and Station here is simply because it's been mentioned the most often in the twist, which is quite like reasonable here. But there's no like critical information there like being extracted by the traditional NLP method. Without a deeper understanding of the twist content, the crucial information are still be hidden behind all those noise. So the transit agency may need a better tool, may need a more advanced tool to fully harness the potential of the social media. This tool should be capable of extracting meaningful information from the large amount of twists, filtering out the noise, and providing some actual insights. And which leads to our object of providing the transit path information extracting pipeline. So we are developing this large language model tool to enhance the accuracy of identifying the sentiment and also the sarcasm of the social media posts. And also we want to expand the analytical dimension of such social media content. And we want to the model to capable to extract some more information, such as extract the geographic data from the tweets when it's available, of course. And by doing this, we want, like in the end, we want to improve the ability to identify the customer needs for the transit agency. The data we use to conduct the experiments here is the twist data collected from February to December in 2015. I know it's quite outdated, but still it provides a lot of insights and ideas of how this system is working. And for the pre-processing step, compare with the complex pre-processing step we have seen, like for using the traditional NLP method, it's only 2 steps. First step, you extract the twist contents and the time step of the tweet, and then the next step is to fill out the irrelevant twist, which is mainly the duplicate twist and also the retwist with less additional information there. So before we talk about the basic pipeline of the information extraction steps, I just want to talk a little bit about the benefits of using the large language model instead of the traditional NLP model. The large language model performed really good on understanding complex linguistic because of it trained on a large amount of data collected from variety of sources, and it's all like currently collected so that it can adapt it continuously to new linguistic style, and it can be better at recognizing non-literal languages. And as for the information retrieval, using the large language model by like simply fine-tuning the prompts you guide the large language model, you can have a deeper and multi-dimensional analysis, and you can process large volume of information all at once. And to do this, you can increase the flexibility and the freedom for your data analysis process. So let's take a quick look at the information extraction pipeline of the transit path. So the first, we start with the prompt structure. So the prompt we have is based on 2 parts. The first one is the system prompts, and the second is the user content. So for the system prompts, it defines the role of the large language model, the task it be targeting, and also the output structure it needs to generate its output. And for the user content, here is specifically a twist from the user. And after we like structure the prompt here, the large language model takes the prompt and will go through a multi-attempt mechanism, which not ask the large language model to only generate one output, but to generate several more outputs here to somehow eliminate the bias from each attempt here. Like for example, for this specific twist, it's basically a passenger complaining like the Wi-Fi deployed in TTC. I think it's in TTC subway. It's really slow. And in the first attempt, the sentiment recognized by the transit pulse is negative, and it's been labeled as sarcastic twist. And in the second attempt, for some reason, the large language model preferred the sentiment to be a neutral, and there are small attempts of those. And after getting all those attempts, which is the text-based information, we will put those into information aggregation steps to further make text search segregation and put them into a structured data set. And then we will go through a consensus mechanism to gather together all those information from all the attempts and to have the most common results from the transit path. So as we can see, the sarcastic will be labeled for the twist will be labeled as true, and it's a negative sentiment. And while we're doing this, we also notice that there's a problem of lacking of domain-specific knowledge for large language model, even though it's quite powerful. In this case, the large language model is missing the specific knowledge about the TTC stop name. So because of that, identifying the station name will cause a lot of mistakes. So the first one, like the large language model considers the TTC as a station, which we know is not a station name. And also it can sometimes take the abbreviation as the station name. And also when the when the station is misspelling it, the transit policy will consider taking this as it was. So to figure this out, we are introducing the RAG system, which stands for the retrieval argument generation system, to add the external knowledge, or which in this case is the station name in TTC system. So the way to do this is first we embedding both the external knowledge and also the user query, which in here is the twist contents, into some vector space. And then we're using some distance measurement to get the station that is most close to the user content. And then throughout the re-ranking system, either the re-ranking system is built by an embedding model or another large language model, and then we can get the final station name. And by using this, we can correct all those mistakes in the first trial. And moving to the task, we use the transit path to do. So the first one is the classification. So we classify the twist by its sentiment and also sarcastic. So we can see on the left of the Sankey plot is the sentiment labeled by traditional NLP method, and on the right is the sentiment label by the transit path. And also in the middle, we have the sarcasm label generated by the large language model, which help us to identify the twist that contains sarcastic content. So we can use this Sankey plot as a cross-validation of the sentiment and the sarcasm label. So we can observe that most of the sarcastic twists are built up from the negative twists detected by the large language model, which indicates that the sarcastic twist often carry a negative sentiment. And in contrast, there are very few positive and neutral twists that are identified as sarcastic, which shows a clear distinction in the labeling consistency of the large language model. And if we compare this with the traditional NLP method, we also notice that the sentiment label are not as consistent with the sarcasm label, which means the traditional NLP method may fall into capture the sarcasm feature of the content. And I want to give you this examples here. Because of the thankful keywords here, the traditional NLP method will identify it as a positive twist, but it's actually a sarcastic by our understanding, and also from the transit pause, it will be labeled as sarcasm and also be labeled as a negative sentiment twist. And moving to the problem information extraction, we're using the transit pause to extract 9 different problem labels, like to categorize the twist into 9 different problem labels. And we are not stopped at there. We further summarize the problem and extract the keywords using the large language model in the transit pause. So as you can see, the first step, we classify the twist and then we extract those keywords. For example, in the first one, for the maintenance problem, you can see the keyword we extracted from the twist is related to somehow like the repair, the broken, and the track and service. It's quite related to what the general problem label is. And by summarizing and extracting those keywords, the transit pause can help us pinpoint some specific problems the passenger is facing and to provide a more comprehensive understanding of the main concern in each problem area, instead of just put the twist into some like relatively general situation. And also with the problem information extraction ability, we can also use that ability to label the dataset. So this is an example of the labeling ability compared between human label and also the label by the large language model. We can see because of this twist, it's initially being identified as a neutral twist. So we somehow, like for human labeling, because of some mistake we made, we classify it as a false because we think there's no specific problems there. But using the transit pause, we can actually identify there's a problem of closure of line 1 because of the real work, and then we put them into the category of there's a problem mentioned in the twist. And also in the other case, when we're doing human labeling, we treat this twist as there's a problem in there, and we classify it as a travel time problem. But actually, there's no actual problem. It's just thanks the driver for wait for the passenger for sometimes. So it's actually like through the transit pause, it being marked as no problem extracted. And lastly, is that using this transit pause, we can extract additional geo information. We can perform a station level performance analysis for the public transit system, which is quite valuable because for most service, like we conducted either online or physical, is more focusing on the system level performance and often lack of location specific data. And in here, we show the twist counts for the 5 most mentioned stations for each hour from 7 a.m. to 11 a.m. And we can observe that the Union Station, the Yonge Station, and the Eglinton Station are frequently mentioned, which reflecting like they are basically the most busiest station in Toronto. But we also noticed that for here, the Bloor Station appears prominently from 9 a.m. to 10 a.m., which may indicate a possible incident or issue at that time. So in the rest of the presentation, I'll just show you how we can use those extract information from transit pause to really give the transit agency some more useful information to identify what is happening at that time. So start with this, we can identify those twists and we classify those twists and we can see those twists are being categorized as travel time problem. So which means there may be some like problem is related to the travel time there at the Bloor Station. And I don't know whether you have remembered like this plot I showed you like early of the presentation. Still, like there's no specific information, and this plot is actually generated based on all those twists like related to the Bloor Station at that time. And if we take a closer look to all twists there, you can see like definitely people are complaining about something, but you have to really look into like what they are writing here. But using the transit pause, it actually can give you the keywords of some useful information. And based on those keywords, you can have a word cloud like this, so that you can notice that there may be an unusual long line for shuttle bus, suggesting a capacity issue during the morning rush hour. And with all those information, the transit agency maybe can further investigate using some on-site cameras and then implement some better solution to address those passenger overflow problem. And with this example, we can see with our advanced techniques, we can provide some actionable insights for real-time problem solving. And for conclusion, with our transit path information extraction pipeline, we can have a better sentiment analysis. We can extract more meaningful insight from the social media, driving from a limited to a rich information. And we can also provide a more actionable information for transit agencies, such that we can drag down from the system level analysis to a station level analysis. And for the future work, we want to build up a more comprehensive data set and to build up to have more people review those to make it more robustness and accurate. And also we want to tune up the prompts we use for generate the results of the transit path. And also we want to make our model more efficient by smaller our model scales. Okay. Yeah. Thank you so much.
Thank you, Joe. That was really interesting. Very cool. I already thought the Calgary project was pretty good, but this is you've really moved the needle. There is a question to clarify the 9 category labels you had. Are you manually providing those like as input, or do they come out of the LLM in order to come up with those categories and then classify the tweets?
Okay, that's a great question. So originally, because as you mentioned, this data is originally using for the Calgary sentiment analysis project, and it actually has a sub data set is from TTC related to it. And we have some manually labeling information in there for 9 different problem categories. And we do that for 2,000 twists at first, and then we extract info keywords for each problem categories. And then we use the keywords extracted for each category to further identify the rest of the twists inside of the data set. So that is where this 9 different 9 problem labels from.
Okay.
Yeah.
Good. So I did have a question. Yeah. So this is, as I had mentioned in my presentation, linking performance with experience. This is very interesting because it's very hard for transit agencies to actually get insights into, they conduct a customer satisfaction survey once a year, and sometimes they'll do an intercept survey, but it's very expensive. So this is really interesting about getting a way of of analyzing data that's generated in an automated way. So what you're saying is that by doing the subcategories of the word maps, you can drill down into the categories a little bit in more detail. Is that correct?
Yeah. So because at first we only have this a general problem set. Right. We can only have we may understand there's travel time problem, but with the word cloud, or maybe in the real world practice, we can make it a more textual, or we can have some other visualizations for the keyword exactly extracted from the twist, so that we can have more information of what is happening on site, on the street. And then the transit agency can action based on that information.
Yeah, great. Okay, well, thank you very much. That was really fascinating.
Thank you.
Next speaker is Roger Chen. Roger, you can start queuing up. Roger recently completed his master's from the University of Toronto while working in the Transit Analytics Lab. He currently works at Metrolinx on the rail service design team, working on the planning and operations of new and existing GO train services. And his topic is investigating post-pandemic recovery trends in subway ridership in Toronto using Wi-Fi data. As I mentioned, there's new sources of data coming up, and there's all sorts of interesting things that can be done with them. So, Roger, take it away.
Thank you, Brendan. Let me just share my screen.
I think it's starting.
Cameron, see and hear me okay?
Okay, yeah, not in presentation mode yet.
Cameron, can you see me
Yep.
okay?
Yep.
All right. Thank you very
Good.
much. Yep, so thank you, Brendan, for the introduction. I'm Roger. I recently finished my MASC here, and yeah, I'll be presenting some research that went into some of my thesis work, so into Wi-Fi data on the Toronto subway, and looking at some post-COVID ridership trends from that. So in terms of, I guess, overall objectives for this research, obviously, to very quickly to understand the shape of post-COVID subway ridership recovery in Toronto. So obviously that's something that's of a lot um, of obvious interest to transit agencies such as the TTC, but also transit agencies more broadly. We want to take a bit of a deeper dive and look at where and when passengers are returning to transit, because we know that there are some emerging post-COVID differences in which specific markets are being responding to COVID and its recovery. And we want to look at it across different, again, how this differs across different submarkets, specifically in terms of OD flows, which is what we're leveraging from the Wi-Fi data. So about post-pandemic, so about post-pandemic trends in transit, obviously since COVID-19 has come onto the scene, there's been a lot of discussion about how it's affected transit, especially in terms of ridership trends. So we see differences in where riders are returning since the pandemic has happened. For example, we see that downtowns in general have recovered most slowly and were the most immediately affected by the onset of the pandemic. We see differences in when riders are returning. So especially we see differences between peak ridership, which tends to remain depressed and is not quite there compared to where it was before COVID. Whereas during off peaks and especially weekends, we see riders returning a lot more quickly, and in many cases have already exceeded 100% of what pre-COVID levels were. And of course, we also see differences in which riders are returning. So looking at demographics, employment, income, those sorts of variables, as well as in terms of trip purposes. Right, so we see that especially discretionary travel has tended to rebound fairly quickly since the pandemic, whereas the work-based commuting, that kind of stuff has tended to lag behind somewhat. So these are, very interesting trends. They're very relevant for transit agencies as they plan their services. But of course, we need some data to monitor these trends in a lot more detail, and that's where the Wi-Fi comes in. So a little bit about the methodology. So this illustrates the methodology of the analysis that we used. So we start with the raw data. So in this case, the Wi-Fi data, which was gathered from the TTC subway system. From the raw Wi-Fi data, we constructed device journeys, so that a device journey is essentially one device trip made across the system. And in a couple slides, I'll explain how we actually determine that. And even with just these raw trips without any further data, we were actually able to get some pretty interesting preliminary exploratory results. And that stuff I already presented in last year's TAL Research Day. And there's a TRB paper that was published based on that. So I can post that link below if anyone's interested. But using these device journeys, then we integrated that with data from the TTC in terms of especially fare gate counts, so entries and exits at all subway stations. And we use those to construct OD matrices at a daily level for the entire analysis period from late 2020 to late 2023. So that gives us essentially a system-wide OD matrix of all 75 by 75 stations in the system. We then aggregated that into subregions of the city, which I'll show in a little bit. That's just to aggregate the data a little bit and to mitigate some of like the noise when you have, a big 75 by 75 matrix. For that, we threw it into a time series analysis, which I will be talking about in a couple of slides as well. And finally, we took the results and sort of interpreted them in the context of what we know about the TTC system and post-COVID travel patterns more generally. So I imagine most of you are probably aware of the TTC system, but if you're not, this is what it looks like. You'll notice I still have line 3 just because most of our data was collected when line 3 was still operational. But yeah, it's 4 lines. We divided into 10 regions, as I mentioned before. Those were selected based on a combination of network topology as well as sort of land use and general travel patterns. So numbered region 1, which is downtown, down here, up through region 10. So that's the rest of the city as part of this analysis. So yeah, so the main thing for you guys to notice is sort of the difference between region 1, which is downtown, and all of the other regions, which is sort of the main distinction I'll be talking about in this presentation. Yeah, so in terms of how the Wi-Fi data actually is collected, so this is how we construct a device journey. The layout of the system is that every TDC subway station has Wi-Fi, what we call access points, located throughout the station at the entrance level, concourse, and platform levels. So if you imagine you enter the subway system with your Wi-Fi enabled device, your device connects to the device at the entrance level, and then as you move through the system, your device reconnects to the access point at now the concourse level and then the platform level as you move through the system. And likewise, when you get to your destination, your device will connect to the platform level access point at your destination, and then the concourse level, and then the exit level. And then once you leave the system, then after a given period of time, we conclude that your trip is finished. And then we take all of those device connection records and we string them into what we assume is one trip. And our assumption is that one trip essentially proxies a ride made by someone using the system. And so that's how we connect and collect the device journeys that we analyzed. So just some more numbers about the system and the data. So we collected data from late 2020 to late 2023, as I said, and we collected data from all 75 subway stations across the system. There's 855 access points across the system, so more busy stations and fewer access points at some less busy stations. From this, we were able to construct about 100 million device journeys, so an average capture rate of about 17% compared to overall system ridership. And that was constructed from 3 billion device connection and disconnection records across the 3 years and the 75 stations. So yeah, a lot of stuff. Let's talk about so just a little bit more detail about how we actually constructed the OD matrices and how we integrated the Wi-Fi and the Fargate data. So if you imagine we take the Wi-Fi data, we conducted the trip imputation, that is when we constructed the device journeys, and then we use that to aggregate that into basically a C matrix. So that's just slicing the data by day and by origin and destination station. So that's why we got the C matrix for what we call the C matrix for every day of the analysis period. And then that's essentially this the square in pink here in the middle of the matrix. Then we took the AFC data, the Fargate data, and we treated those as control totals because we know that the Wi-Fi is only sort of a sub-sample of the overall system ridership, of course. So by taking the Fargate data and treating that as the ground truth, then we're able to scale up the rows and columns of the C matrix using an iterative proportional scaling method. That way we have a matrix that, as closely as possible, sums across columns and rows to what the actual ridership estimated at each station is based on the Fargate data. And from that, we obtained the balance matrix, and that's what we used to feed the time series analysis, which I'll now talk about. So in terms of the time series analysis, there are a number of sort of competing models. If you're familiar with time series applications and if you're familiar with that kind of machine learning, for this one, for this research, we adopted something called the profit model, which was a model developed by data scientists at Facebook. It takes the form of a modular regression model, which is based on essentially just an additive time series decomposition. So if you imagine we have a time series, so a set of ridership over time, we can decompose that into several components. So we have the trend, which is sort of the overall direction of where the data is going. We have the seasonality, so cyclical effects that repeat, for example, by every week or over the course of a year. We know, for example, that summers are typically lower ridership, fall is higher ridership, and then within the week, we know that weekends are tend to be lower than weekdays. Something that's somewhat unique is that Profit also accounts for holidays, which is, as the name suggests, it lets you account for sort of these one-off deviations from the overall seasonality effects, but also allows us to capture sort of one-off other disruptions. So things like data issues we're able to capture, or other sort of effects that we want to quantify, but we don't anticipate are recurring. So that we wouldn't be appropriate to model with seasonality or other effects. And then we have the error return, of course, as always. So there's a number of reasons why we chose the profit model specifically over other models. I'm going to highlight that profit is actually developed it's sort of tailored for less, I guess I should say more industry-focused applications. So it's designed to emphasize being able to handle realistic holiday structures. It's designed to be more interpretable than some other models, such as ARIMA or its derivatives. And it's designed to handle, and it tries to, relax as many assumptions on the underlying time series as possible. So we can handle things like non-stationarity and that kind of stuff very well. So yeah, that's it for methodology. Okay, so we'll jump into the results now. So I think it's probably a good idea to start with sort of what the shape of system-wide ridership is. So here I basically just plotted for every single day over the analysis period from late 2020 to 2023, with the daily ridership both observed and fitted according to the time series is. And so you can see the blue line is the time series and the black dots are the actual ridership. You can see that overall it fits quite well, which is good. So what we expect from gives us some confidence in the results that we're getting. I alluded earlier to one special feature of the profit model is the holidays term, which allows us to handle one-offs or allows us to account for one-off events without skewing the overall model estimation. And in this case, we can see that it does that quite well when we're looking at things like the impact of the Omicron wave, which was in early 2022 when there was suddenly, another wave of lockdowns that quickly went away. But we can see that this allows the model quite well to handle that sort of temporary one-off event without skewing the estimates for, without, erroneously thinking that there will be a similar effect at that time of year in other years, which is what we don't want and what would really harm the estimates for that time of year. So yeah, this is good. It shows incredibility in sort of what the model is doing. So as I said, so what I just showed was the fitted model as a whole, so including all components, but recalling that we can decompose this model. That's why sort of what we adopted Profit to do. Here we're just extracting the trend component for system-wide ridership. And we can see that it's much smoother, so it's a lot more interpretable, I guess. And something I wanted to highlight specifically is that we can actually divide this into sort of 3 distinct phases. And this is something that holds true more or less when we look at not only the whole system ridership, but also when we look at ridership by different submarkets in the city. These 3 phases, I've sort of labeled them for discussion. The first one is the pandemic, or what I call the pandemic, quote unquote. And that's the early stages of the pandemic, late 2020, early 2021, when everything was still, broadly speaking, locked down and there was not a lot of travel going on in general. So ridership was low, it's stable, it's even slightly decreasing over this period. Then there's the recovery period, and that's sort of when we see the fastest return of ridership to transit. It goes on at different rates in different submarkets, but as a whole, this is a period from mid-2021 to late 2022, early 2023. That's when we see the bulk of this ridership recovery. And the end period is what we call the new normal, or what I'm calling the new normal as a name. And that's sort of when this recovery tends to somewhat stabilize from early 2022, or sorry, late 2022, early 2023, and so on, when the rate of recovery is slowing down and sort of trends are sort of stabilizing at this new normal, quote unquote. So of course, as I mentioned before, one of the strengths of Wi-Fi is that we are able to use it to look at different OD pairs and look at how there are variations in ridership from a geographic perspective. And so this shows what's going on here. So here I've just superimposed what the ridership recovery looks like over the analysis period but this time it's broken down by not just at a system-wide level, but also the yellow line is intra-downtown travel, so travel within stations in the downtown core. I have green, travel between downtown and the rest of the city, and in blue is non-downtown travel, so travel between stations outside of the city core. And so in the beginning in 2020, we can see that intra-downtown travel lags behind the most, the others. And that's consistent with what I think most operators have seen. But then as the recovery progresses, they all return at a similar trend. But as we get closer to the end of 2023, even going, what we see is that intra-downtown travel, even though it was the lowest at the beginning, has actually recovered the fastest as well. And it's actually at the point where it's actually overtaken travel between downtown and the rest of the city, which, according to what we've seen, is actually somewhat starting to stagnate since about mid-2022. So this is showing, again, sort of what the how we're seeing kind of different trends between we look at different submarkets. We also see different trends between submarkets when we look at not just the trend terms, but also the seasonality term. So here we are showing estimates for what the sort of specific effect is per weekday. So comparing Mondays versus Tuesdays versus different days of the week. And of course, since COVID, it's been sort of widely reported on that as a result of that, since COVID, in large part due to things like remote work and hybrid work, we're seeing sort of intra-week variations emerging. So where people are choosing to go into the office on in the middle of the weeks, Tuesday through Thursday, and whereas they're staying home on Monday and Friday, I guess to give themselves maybe a longer weekend, effectively. And we see that as well in the ridership. And we see that Fridays and Mondays are lower than the rest of the week. What's also interesting here that I want to highlight is that when we look at intra-downtown, the estimates for intra-downtown travel, we see this effect to be even more exaggerated. And what we're thinking is that travel downtown is the most strongly affected by commuting to all of the offices downtown, and those tend to be the ones that are also most affected by things like remote work. So it's interesting to see this effect, which is consistent with what operators have been observing, reflected in this data as well. So to end off here, I want to talk about a little bit of what in terms of future forecasting that we've done. So this is a time series model, so obviously we can take it and extend it a little bit into the future as well to see what could happen in the future. So for this, we've adopted a 6-month forecasting horizon, and that was based on a little bit of trial and error. We wanted to balance if you forecast in the shorter term, you get greater confidence in your results, but that's sort of less useful if you're a transit planner trying to forecast the future. So given these requirements, we adopted 6 months as a bit of a compromise there. So we applied the model for about 6 months out from end of 2023 into June 2024, and we forecasted about 1 million daily weekday system-wide boardings, which was actually borne out quite closely by actual TTC's ridership stats from June 2024. So again, that provides even more confidence in the overall results of the time series models. And in terms of differences in demand by submarkets, we do continue to see slowing growth in demand between downtown and the rest of the city compared to the other subsectors. And again, that's consistent with what I just presented earlier. So there's a lot of things that all provide sort of confidence in what these models are doing. So just to recap in terms of key findings, we've shown that Wi-Fi can be used to track riders' origins and destinations across the subway system. In terms of submarkets, we saw that downtown saw the greatest ridership loss initially, but it's rebounded the fastest due to discretionary travel. We've seen that, again, more generally, the ridership is returning at different rates between different submarkets. Using the time series analysis, we found that post-COVID ridership recovery, we can divide it into sort of 3 distinct phases, which hold true no matter if you're looking at a system-wide or at a submarket level. And all of these are consistent at some level with what has been found elsewhere by agencies as well as other academic research on how the pandemic has affected transit. So all in all, it's some interesting findings that sort of drive well with what has been found elsewhere. So where do we go from here? Obviously, I think our time series models that we did, they're interesting, but there's also a lot of room to identify additional data sources as regressors, and that might allow us to tie these trends in ridership to more specific elements, such as office occupancy or retail activity or other sources of activity. We want also to adapt the OT estimation process to not use perhaps just Wi-Fi, but also other data sources such as cell records. As you may have heard, the Rogers and the TDC are looking at discontinuing the existing Wi-Fi system on the TDC due to the advent of cell access and lower uptake of the Wi-Fi system in general. So this is something that could be necessary if we want to use this analysis method going forward. We also want to refine sort of the future forecasting capabilities. It was sort of an addendum to my research, but obviously there's room for a lot more research in that direction as well. And also something else should be important to note is that if you're familiar with the TDC network, it's not just the subway, it's also the streetcars and the buses, and they provide a lot of really vital transit coverage in the rest of the city. And so it's really important to see if we can do a similar analysis to those modes as well to get a better picture of, it's not just the system, not just downtown, but also how the rest of the city is responding. So before I end, I know that this is mostly practitioners I'm talking to. So of course, this question of what do we actually do based on this? And so there's some, I think, conclusions that I think follow from the results that I've presented. So first of all, I think we should reorient our transit networks. I know historically they've been tended to be very peak commuter oriented. So things like the GO transit system, for example, used to be, into the city in the mornings, out of the city in the afternoon, and that was it. And COVID has shown that that's sort of not a sustainable model for transit going forward, given that that is the transit share that is recovering the most slowly. And so there should be some thought given to, how do we convert our transit systems into transit networks that serve greater variety of purposes, especially the ones that are recovering the fastest after COVID, instead of just the ones that are sort of recovering the slowest. Similar to this is changing planning policies in general. So there's been a lot of research, not just from my research, but also others in this vein that have looked at how users' attitudes and usage and travel habits since COVID have changed. And there's been a lot of interesting recommendations that have been thrown around regarding how do we change our priorities of transit agencies, as well as fare policies to sort of entice riders back on, and policies that will better match how people are using transit now. Another thing that is worth exploring is looking at new data sources. So I think this research has shown the value of Wi-Fi as a data source that's able to give you some very valuable insights compared to more traditional data sources. So again, this is going back to sort of what Brendan was talking about, but if there's room for leveraging these data sources, it should be appreciated. And finally, this is something that's, I guess, considering the fact that it's late 2024, almost 2025, we're about 4 or 5 years out from the start of the COVID pandemic, and it's, I think, at this point worth asking the question for agencies and for data scientists in general: is it worth, is it still worth talking about things in terms of a pre-COVID baseline, or is it worth talking about, or do we consider, this a new baseline that transit is recovering from, or the transit has already achieved? I already pointed out that there's some submarkets that have already achieved 100%. So, to what extent are those still recovering? And there's also the fact that there's not just one recovery; different submarkets are recovering at different rates. So it's, it further begs the question of, is it worth talking about a single recovery? So, again, an interesting discussion to be had, I think, that is raised by this discussion. Yeah, so that concludes my presentation. I want to acknowledge BAI and the TDC for giving us data access for this research, obviously. And yeah, I'll be happy to take any questions for the next couple minutes. Thanks.
Thank you, Roger. That was really interesting. I noted that one thing I did not realize is that Monday is even lower than Fridays, which I'm not sure I understand the logic of that. I would think they would be pretty much the same, but you have any insights on that one?
Yeah, you're talking about this one, right?
Yeah.
Yeah, that is a good observation. One thing that comes to me at the top of mind is that when we're looking at ridership that's due to commuting versus due to discretionary travel, Mondays tend to be just commuting. There's not you don't think of like going out on Mondays as much, right? Whereas Fridays are
Okay.
going into the weekend, and we do actually see. So this is drawing my experiences both with Stata as well as I currently work for
Yeah.
Metrolinx. But we do see some like more ridership on Fridays. That's due to this kind of discretionary travel. So again, that's not something that we really teased out in this analysis. But if you think about like people on Fridays, they're not coming in so much to the office, but instead they're maybe coming into the city for an evening and then going home late at night. That could be something that's driving, it's booming in the Friday ridership we don't see in the Monday ridership, for example. So that could be something as well.
Yeah, well, because it'd be a lot more entertainment travel.
Right, exactly.
Although Michael think that has changed in the past year, and Fridays now lower than Mondays. And I'm not sure. There was one.
I mean, sorry. Yeah, that is possible. This, as I was saying, this date extends until end of 2020 or late 2023. So again, there has been almost a year since then that isn't reflected here. So it's possible that there's some change there as well. But
okay, we're running a little late. I'll take this one, and there's one other, Roger, you can answer in the chat. I know there's also a discussion about transfers, but not sure I missed this, Roger, but are you taking into account fluctuations in population size?
Yeah, that is so like you're talking about like population overall.
I guess, yeah. I mean, part of the recovery is not just people that were there before coming back, there's immigration as well.
Yeah, this is something that it's something I touched on in my thesis whenever that comes out. But we did like obviously it affects different parts of the city more than others, right? So if I may go back, so obviously there's some. So when we look at overall or I guess population and demographic trends over the city, there's some areas that are fairly stable or even declining, and that tends to be more so like the inner suburbs. And then the regions that are really booming are for one, downtown. There's a lot of condos that are being built, as well as more suburban outlying areas, especially in the northwest, like Region 10, which is the extension that goes up to Vaughan. In that one, we actually did see sort of a higher than fast, like a faster rebound than the rest of the city. And we did, hypothesize that is in part due to greater population growth in that region, as well as, larger demographic differences in different parts of the city. But
the opening of Finch West may even stimulate that even more so in the near future.
Yeah.
Okay. Well, thank you very much, and we'll better go on to our next speaker. Next speaker is Mohammed Ansari Esfe. He's a NSERC PDF postdoctoral research at the University of Toronto. He earned his master's and PhD from the University of Calgary. As a researcher, he has been involved in several industry and consulting projects and focuses on various subjects, including urban system resilience and vulnerability, public transit modeling, ITS behavioral modeling, and big data analytics. And his topic is evaluating factors affecting user path performance in metro networks, case study of the Toronto subway network. So Mohammed, are you there? And you've got it already.
Yeah, thank you.
Take it away. Take it away.
Yeah, thanks. Hello, everybody. I'm Mohammed Ansari, and today I'll be discussing evaluating factors affecting path performance in metro networks with a case study of the Toronto subway network. So this is an ongoing research, so I would appreciate any questions, feedback, and comments. So public transit is among very few transportation modes that protect qualities that we value in our society, including equity and sustainability. So access to reliable public transit is crucial to all users. However, subway networks, very similar to other transportation networks, are prone to disruptive events. And these disruptive events can be of any type, for instance, train failure, signal failure, power failure, and so forth. And also in terms of severity, they can last from a few minutes to several hours. So previous research on evaluating factors affecting the severity of the impact of disruptive events is very limited. So previous research mainly looked at the effect of incident type, time of day, and also the location of the incidents. However, there are many other factors whose effect on The severity of the impact of disruptive events needs to be evaluated in the context of subway networks. So these are factors that we are evaluating in this study. So these are the factors that may affect network path performance during network disruption. And we have categorized them into 3 different categories. So we have incident characteristics, variables related to incident characteristics, which include incident type. For instance, we can have passenger-related incidents, for instance, having injured passengers at platform or disorderly passengers and so forth. We can also have technical incidents such as signal failure, power outage, and also we can have operational incidents, for instance, when there is no operator available or when the station is skipped by mistake by the operator. So these are operational incidents. Also, another incident characteristic variable that we are considering is incident duration. So for how long the effect of the incident is persistent in the network. So that's also another factor that we are looking at. Also, we are looking at a temporal factor, which is the time of day in our study, peak period and off-peak period. So we divided the whole day into morning peak and evening peak is like the peak period, and the rest of the day is off-period time. And we also considered 3 different factors, variables associated with path characteristics, such as path lengths in metro network. So we can have longer paths or shorter paths. And path, I mean, the length of the path in this study is defined as the number of stations included in the path. So for instance, if the path length is 7, it means that there is like 7 stations in the path, including the origin and destination station. Also, whether the path involve an interchange or transfer. And also, we are considering line association. So the path, so we're looking at which path, which station, which line basically the path belongs to. So that can be also another important factor that can affect the performance of the metro network during disruption. In terms of objective and scope, so the first objective of this study is to evaluate factors affecting the severity of the impact of disruptive events, and also to identify which factors contribute more to the severity of the impact of disruption. Also, to develop policy recommendations to improve network resilience. In terms of scope, we are only considering incidents taking place in subway system, Toronto subway system. So, I mean, it's going to be just a study devoted to the subway system itself. Right. So for future research, maybe we can consider the interaction of the metro system and other systems like the streetcar system and bus system. But for the aim of this study, we're just focusing on incidents taking place in subway system. To give you a quick overview of the methodology, just consider this hypothetical network that can be, for instance, a subway network, right? And these are the stations, 1, 2, 3, 4, and so forth. And these are the segments, subway segments. So the travel time of every path in a network can be shown as a distribution, a probability distribution function, basically. So for instance, in this case, the path between station number 3 and station number 6, which is 3, 5, 6, can be shown during normal operation as the blue curve, right? So this is the distribution. So instead of just reporting an average value for the travel time of this path, we can basically draw or obtain a distribution of the travel time during normal operation for this specific path for a given time interval. Let's say, for instance, for 1 hour time interval, 2 hour time interval, and so forth, right? So it depends on the within day variation. I mean, how accurately we want to capture the within day variation and day-to-day variation in travel demand, right? If we want more granularity, for instance, we can go with 1 hour time interval, or we can do it, for instance, for peak period and off-peak period. Similarly, we can obtain the distribution of the travel time during network disruptions. Assume that we have an incident going on in a network at station number 4, right? So we can still, for this case, also obtain the distribution of the travel time for this specific path, which is shown as the red curve, for which we have likely a shift in the mean value and median, right? So we can do this for all paths in a network, right, including the paths that include the station 4. And again, we can obtain the distribution of the travel time during normal operation shown by the blue curve, and the one during network disruption shown by the red curve. And we can compare these two distributions to assess the extent of the effect of network disruption. And we are doing this using by estimating limited state function value. So limited state function value is basically a concept that we borrowed from a structural reliability analysis and applied this to the context of transportation network analysis. So LSF basically measures the extent of the effect of incidents in the term that it basically estimates the probability that the travel time during the incident is higher than the travel time of a path during network disruption. So to do this, all we need to do is to find the PDF, the probability distribution function of the two journey time distributions, one for normal operation and one during network disruption. For this, we are examining log logistic, log normal, and truncated normal distribution. So these are the distributions highlighted in the literature as best describing the travel time distribution for subway networks. And then finally, we perform a crude Monte Carlo simulation to estimate the LSF function for every path in the network. For the analysis, we are using two data sets. We are using Wi-Fi data. So Roger provided a comprehensive introduction to the Wi-Fi data. So basically the Wi-Fi data captures individual journey times, right? And we are focusing on Toronto subway network. It records up to 30% of the daily subway trips, so it's very representative of the travel pattern in Toronto subway network. We do have access to the data from September 2020 to September 2022, but for the aim of this study, we are just focusing on data the entire 2021 because that's the most reliable portion of the data that we have access to. And because it captures individual journey times, it also captures experienced extreme travel delays that the Toronto subway network historically encountered. We also used incident data. That's another database used in this study. And it contains historical records of subway incident. And it includes details on date and time of the incident, type of the incident. Again, there are about 129 different types of incidents in the database. We have just reduced the numbers. We have categorized them to three main categories: passenger-related incidents, technical incidents, and operational incidents. We also have information about line and stations affected by the incident, and also the duration of the delay, the amount of the delay incurred by the system resulting from the incident. Just in the year 2021, we had 7,219 incident records that we analyzed for this study. So just give you a quick overview of the results. We ran a multilinear regression model. So in this model, each observation is a path in a network and the corresponding LSF value. And the response variable is the limited state function value. Again, that measures the extent of the effect. And the predictor variables are the ones that we have discussed so far. So incident duration, incident type, time of day, path length, whether the path involves a transfer or interchange, and to which subway line the station subject to the incident belong to. And these are the results. So as you can see here, so this is the effect of peak. So all of these coefficients, so these are the estimated coefficients from the regression model, right? And we have different categories of, let's say, variables, temporal variables, path characteristic variables, and incident characteristics, variables related to incident characteristics. So as can be seen here, all of these values are positive, which means that positive is significant, which means that they affect the severity of the impact of disruptive events. Right. So during peak period, so it seems that incidents during peak period have a more severe impact on network disruption compared to incidents occurring during other times of day. Also, when it comes to path characteristics, so path with transfers, paths involving interchange are affected more severely by incidents compared to paths that they don't have any interchange stations. So that's kind of intuitive because we can have path in a network with transfers, and these transfer, and we can have incidents in these transfers and interchange stations. And these interchange stations are very critical points in a network, which means that when we have a disruption in these stations, it's going to affect multiple lines, multiple passengers in a network. So that's kind of intuitive finding when it comes to the effect, finding the effect of incidents on paths that involve transfers. Also, paths that are on line 1, this is basically Young University line, they are more affected severely when there is a disruption in network compared to path on line 2 and line 4. And the difference is very significant, basically. That's also kind of intuitive because line 1 is the busiest and oldest metro line in Toronto subway network. So there is a higher probability of occurrence of passenger-related incidents and technical incidents. So these factors basically contribute to more to vulnerability of line 1 in Toronto subway network. Also, paths with longer paths in network are basically more affected by incidents. When it comes to incident characteristics, we found out that passenger-related incidents are basically affecting the network performance more severely compared to operational incidents. And this is very problematic in Toronto subway network because I mean the majority of the incidents in metro network is also they are passenger-related incidents. About 66% of incidents in Toronto subway network are passenger-related incidents, and they are basically affecting network more severely compared to other types of incidents in a network. Also, we found that incident duration has a positive effect on network performance. So incidents that are of higher duration basically affect network more severely, but the impact is kind of not as significant as the other factors in our study. So to further evaluate the effect of the continuous variables, which are the incident duration and path length in our study, we ran another model, which is generalized additive model. It's an extension of linear regression model, but it allows for nonlinear relationship between predictors and the response variable. The response variable is the same here. So we have the LSF value for a path, but the predictors here are the incident duration and path length. So if we plot this using the generalized additive model, so these graphs on the y-axis, we have change in the LSF value, limited state function value. On the x-axis, we have path lengths and also incident duration. So as can be seen here, as the path length increases, the impact of the incident on past performance increases until a certain point, which is about 7, path lengths of 7. But beyond this point, we have kind of a decreasing pattern, which means that for very long paths in a network, the effect of they are less affected by this disruption. And that kind of makes sense because I mean, longer path, the effect of the incident is being offset by including more stations, right? So this way we can kind of justify why this behavior is basically observed for longer paths in a network. When it comes to incident duration, it's not as straightforward. So as you can see, we have kind of a decreasing pattern. So incident duration is per minute. So for about, when the incident duration is about 2 hours and 30 minutes, so we have kind of a decreasing pattern. So which means that incidents with less than or equal that last in a network for about 2.5 hours or less than that, basically the effect of their effect is kind of it's still significant, it's still positive, but the impact is not as significant as the incidents for which the duration is about between 2.5 hours and about 4 hours in a network. And after 4 hours, we are going to have a decreasing pattern. So I'm still working on this to see what could be the cause of this kind of bumpy curve. But these inconsistencies can be attributed to the type of incident and also the time of day for which the incident occurred. As summary and conclusions, so in this study, we evaluated the effect of various factors on the severity of the impact of incident with a case study of Toronto subway network. So we found, so these are the major findings. So path along line 1 are more severely affected by incident. And as we discussed so far, line 1 is the busiest line in Toronto subway network, and it's already running above capacity, especially during morning hours. and it's the oldest one, right? So being the busiest and the oldest one basically increases the chance of passenger-related incidents and also technical incidents. And sometimes, since we have more frequent service, there's a higher chance of operational incidents as well, right? So it requires, for instance, if we want to improve the service and resiliency of line 1 network, it requires more emergency response unit along line 1, for instance, than other lines when it comes to prioritizing resources to improve the resiliency of Toronto subway network. We also noticed that passenger-related incidents cause more severe impact on the network performance for the case of Toronto subway network. As I said before, more than 60% of incidents in the subway network, Toronto subway network, are passenger-related incidents. And the good news is that we can do something for passenger-related incidents. So these are sometimes related to, I would say, disorderly passengers, having injured passengers, and so forth. So we can allocate more resources to reduce both the frequency and also improve the response time to these kind of incidents in Toronto subway network. So we don't have, we have no control on technical and operational incident occurrences. So operational incident occurrences are very random, and technical incidents, to prevent them, we have to invest in the infrastructure, which is very cost intensive. But when it comes to passenger related incidents, we can do it by education and allocating more resources, and hopefully increase the resiliency of Toronto subway network. The next steps of this study would be driving a vulnerability index based on the limited state function value. So basically, using this vulnerability index, we are aiming at identifying vulnerable subway paths and stations in subway networks. This new vulnerability index would measure the deviation of travel time during disruption from the usual travel time, and it also captures the temporal impact of the disruptive events. Also, we can combine this LSF analysis with other vulnerability measures, such as network efficiency, to capture both the spatial and temporal impact of disruptive events. So these are the topics that we're working on it, and this is going to be a part of this analysis to see which stations in general we have to improve the operation to increase the resiliency and vulnerability and reliability of Toronto subway network.
Thank you, Mohammed.
Thank you very much.
It's good to see more and more research about disruptions, because disruptions are the major source of annoyance to passengers. And I know Amer's group did some work on the bus bridging previously, but this is drilling down to the causes of the incidents is very useful. I'm going to make one comment, two comments. One on the passenger ones. You mentioned disorderly passengers, but I think a major issue is suicides, and that's to deal with that, you have to go to platform doors. Secondly, the technical one, I think you want to be a little careful, because I think there are things you can do. Yes, if it's related to the track alignment, which is causing current slowdowns, yes, it's very expensive. But if it's dealing with vehicle breakdowns, then preventive maintenance or reviewing maintenance procedures is a short-term solution that would not be as costly as trying to have to invest in infrastructure. But thank you very much. And we're going to go to the last speaker. Jedwin Mock. First I'm going to say we're going to run over, but please hang in here, because this is very different and very interesting. Jedwin Mock was a research fellow at Metrolinx, where he aimed to help the agency understand the factors behind transit construction cost escalation, which is a big issue. In addition to being a researcher at the Urban Cycling Institute in Amsterdam, he currently serves as a creative director of City UX, an urban consultancy based in Estonia, and directs this YouTube series, Navigating Urban Transit, on transportation in European cities. And he's going to present some of the information about transit capital costs. So, Jedwin, are you there? You've got it all set up?
Yes.
Go ahead, take it away.
Can you see my screen?
Yes, we can.
All right. Thanks so much, Brendan. And thanks, Mohammed, for that great presentation. My name is Jedwin Mock. I was a former research fellow at Metrolinx and a graduate of the University of Toronto computer science program. And I've had the pleasure of working for the past year on this alongside my former advisor, Balthazar Crane from Metrolinx, Dr. Marco Kitty from McGill University, and Dr. Anna Shalaby from the University of Toronto. And our study goes into, why are things so expensive? I think that's the question on everybody's mind, because our transit projects are way too expensive. And so let's get into it. Hopefully this presentation will answer some questions. So to give you some background, Toronto's a city in a huge infrastructure deficit, right? We're one of the fastest growing cities and metropolitan regions in all of North America. And that has huge implications on our transportation system. Our subway is chronically overcrowded. We have crippling congestion. And also our housing market is under strain. And it causes people to travel further and further away, have longer commutes to look for cheaper housing. So, to close the infrastructure gap, you can't just build any infrastructure. And my proposition is that rapid transit is a key solution. So fast transit is a key solution to closing the infrastructure gap. I love telling the story of Paris because it's such a city with quite a similar income distribution to the city of Toronto, where the outer suburbs, dominant minority groups, they have disproportionately lower incomes compared to the city center. And Paris used to have the same problem that the city of Toronto had, right? Like long commutes from the suburbs, a lack of fast infrastructure to get people to their opportunity and their jobs. And when the Paris RER was built in the 70s, it created almost this fast regional railway. Anyone can get on it, democratized fast travel, especially for people in those outer suburbs. And it created greater access to opportunity. So it's really key that we build fast, rapid transit to serve our growing city. And of course, we're doing that. The Toronto region is undergoing the single largest rapid transit expansion program in North America. On the left is the Crown Jewel project, GO expansion, which is trying to do what the RER did, 50 years ago. And Ontario Line, of course, our new downtown subway, which will tie all of our projects together. But the problem, of course, is that, right, these projects are way too expensive. What you're looking at is a chart of the per kilometer cost from the 50s to today. And all these costs are inflation adjusted. You can see since the 50s to about the late 90s, subway construction costs actually stayed quite steady and tracked with inflation in Toronto. And the Yonge subway, for example, was built for just under $100 million per kilometer, which is 7 times less than the 2019 estimate for the Ontario line. And when we look at the exponential rise in the growth of transit capital costs in Toronto, you can see that the current estimate for the Ontario line is almost double that at 10 times the cost of the original Yonge subway, over $1 billion per kilometer. So there's a couple of ways that we react to this, and this cost crisis isn't just limited to Toronto, it's spread throughout the country. And in Calgary, for example, they have the Green Line, which is a new light rail line that runs between the city and suburbs. It escalated in cost so much that even after they cut the project in half, the cost still went up by like 2 billion Canadian dollars. And their reaction was, well, it never gets cheaper to build major infrastructure projects. So why should we care about costs, right? Like, we should just build the projects now. Well, as projects increase in cost, the benefits are still the same. So the benefit cost ratio of your project drops and drops and drops. And it's harder and harder to justify the construction of these projects. And that's what happened in Calgary, right? A conservative premier canceled the Green Line, a few weeks ago. And my contention to you is that high costs are not inevitable, right? Low costs are absolutely possible in the Canadian context if we want them. And 3 projects from the last 15 years show us that this is possible. The Vancouver Canada Line and Montreal REM, 2 metro projects that really pioneered low-cost construction and are on par with the lowest cost projects around the world. And Waterloo's Ion LRT, which is also in line with other tramway projects in Europe. So we have to understand, what are these projects doing that we're not here in Toronto? And that's what our research is going to attack. So let's start with our research questions. The first is, how can project planning and delivery be reformed to build transit faster and cheaper? And the second is, how can we refine cost estimations in early stages of the planning to improve the way we prioritize projects to reduce those cost-driving planning choices? So our study followed a very, very standard methodology. We started with our research questions, went to an extensive literature review, conducted over 30 qualitative interviews with industry and academic experts. We did a global benchmark then to compare Canadian costs with other costs around the world, and you'll see that in a second. Then we conducted 3 Metrolinx case studies. Now, unfortunately for commercial confidentiality, I can't say which 3, but we did detailed case studies into the project delivery practices at Metrolinx, and then we came to some recommendations. So let's start with the global benchmark. We compiled a data set of 1,083 rail transit projects across 60 countries between 1971 to a projected completion date in 2036. All of the project costs are adjusted for inflation and purchasing power, so we can compare them. And of course, the data is compiled from 4 publicly available sources. The Transit Cost Project, led by Eric Goldwyn, Center for Transportation, led by Ronnie Avas, Stephen Witkins, and of course, Metrolinx. So some people would say, well, high costs in Canada are because countries with authoritarian governance have easier time acquiring land, or countries with low GDP have lower costs. Well, this is not the case. So the chart you're looking at is just the isolated OECD developed nations in our database. And you can see the lowest cost countries are Spain, Italy, South Korea, and Turkey. Those are, all developed countries with high GDPs, similar to Canada and the US. And of course, just to give you some context, the Shimbundong line on the top right is a mostly underground 6-car regional rail line. It's fully automated. It's an express metro, and it costs, just over half of what the Finch West LRT costs per kilometer in Toronto, which is a surface tramway. And some other people would say, well, it's cost of living and labor, right? Like Toronto's an expensive city, Canada's an expensive country to live in. Well, if we look at the Nordic countries like Denmark, Finland, Norway, Sweden, they have some of the most robust welfare states in the world. They have incredibly high wages, but also incredibly high cost of living. And yet they can also deliver projects at 1/5 to 1/10 the cost that we do here in Canada. And lastly, a lot of people have told me, well, it's because our projects are really complex, right? Like downtown Toronto, it's a maze of utilities, costs us a lot of money, and there's a lot of risk involved. Well, all these low cost and Nordic countries, one measure of the complexity of a project is the amount of tunnel being used. And the low cost and Nordic countries build the same or greater proportion of their projects underground. And of course, they're dealing with significantly older cities. Like Italy is putting a metro line under the 2,000-year-old Colosseum, right? The city of Toronto is like 200, 300 years old. So other countries build more complex projects at lower costs. So what's the through line here? Well, every country with a transit project over $1 billion per kilometer speaks English as its primary language. Now, if we stop speaking English and we all start speaking Spanish, that wouldn't solve our cost problem. But this is more to say that, the costs of a project are not tied to these kind of external factors. They're tied to our project delivery practices, the way we govern projects and our institutions in these countries. So Australia, Canada, Hong Kong, New Zealand, Singapore, UK, US, we all go to the same conferences. We all look to each other for new practices and thoughts, and we learn from each other. And it's almost like we're in a bubble. We've created a cost bubble. And you can see this trend further reflected if we look at the distribution of costs across countries. In Turkey, South Korea, Italy, and Spain, costs have, inflation adjusted, have, either remained steady or declined over time, while in Canada and the English-speaking world, they have increased exponentially. So it's time to question, what do we consider best practice, right? A lot of times we refer to the UK and Australia, like Infrastructure Ontario likes to cite the Sydney Metro and Crossrail as projects of, high quality. Well, they were nice, but they were also extremely expensive and over budget. So this is a great quote from our literature review: because the greatest innovation in the high quality, low cost public works is not really in any country where English is the primary language. North American governments should maintain global curiosity. So let's get into what drives cost. We have time for 2 drivers today: design choices and, of course, procurement and management, so actually delivering the project. We'll start with design. So our study has found that, Canadian transit agencies tend to overbuild their projects. Partially, it's because of stricter interpretations of safety standards, right? If we look on the left, You can see a single bore tunnel in the Toronto Scarborough subway extension. And it's significantly larger than the single bore used in Milan's M1, partially because we read the NFPA 130 fire requirements and we thought there had to be a fire separation wall. And it significantly increased the diameter of bore, which increases cost by a large margin. We also have a lack of standardization. So if you compare Milan's M5 with Toronto's Vaughan extension, M5 has these very Spartan standardized stations. They all look the same. They're like $11 million each. And in Toronto, we went for this kind of bespoke custom designs to fit every neighborhood context or whatever. Oh, that comes with a significant price increase and almost 10 times more. And of course, lastly, we like to buy political support. On the left is the Yonge North Subway extension, which when homeowners in Royal Orchard, a very wealthy community, protested because they were scared that tunnel boring machines under their house would shake them, Metlink caved, and we said, okay, we'll dig 10 to 20 meters deeper because you guys are scared of tunnel boring machines. And often this is a risk-averse perception of political support and not actually guarantees any of it. So low-cost projects avoid overbuilding. Instead, from tunneling, they choose low-cost tunneling methods and they avoid tunneling wherever possible. With stations, they try to build as small of a station as possible to reduce the amount of excavation. With right-of-ways, they try to acquire as much existing right-of-way and reduce the amount of land acquisition. That's how the Montreal REM was so cheap. And in standardization, of course, we covered that they standardize so that lessons can be transferred within the project, but also to other projects in the project delivery pipeline. So let's actually deliver the project now that we have the design. So the AAC manual, which is like a cost manual we use in North America, every kind of North American every English-speaking country has their own flavor of this. Australia uses the Ernst & Young P90 method. What these do is it tells us how much we think a project is going to cost. So AAC says, well, we're trying to achieve an 80% cost confidence interval that the project is going to come sort of within a range that we set. Okay, so the explicitly stated goal here is to make sure that the project comes under budget rather than manage the actual absolute cost of the project. So let's see what that does. So we start with our design choices that choose the hard costs. Well, okay, North American agencies are extremely reliant on professional services. So that means private external consultants. We add a 20% premium on top of our design choices. Now, this is completely arbitrary. And then, to manage the project risk, what if something goes wrong? What if we run into, difficult soil conditions or whatever? We add a chunk of money called contingency, which is basically in case things go wrong. And again, it's a percentage on top of the percentage. So we are multiplying the design choices and professional services by 35% and slapping that on top. We then have the post-contract contingency, which is very common, which is to sort of manage the litigation around these projects. And then we go to escalation, which is the inflation of a project. We try to run these complex models that try to predict what the inflation rate is going to be for the next 10 years. It's between 2 to 5% year over year. Now, if I could predict the inflation of the next 10 years, I would be working in Warren Buffett's office, probably not in transit. And of course, then we add property and taxes. So what you end up with is a project budget where only 35% on average of the hard costs, right, the costs that are actually building the project, make up a project budget, while the rest of the budget, 65% is soft costs. So that's to cover project delivery processes. And so what we find from our research is that the proportion of soft costs in North American projects significantly exceeds comparable projects in other developed nations. Right on the left is a graph of an average of about 6 North American projects from Toronto to Montreal to Los Angeles. We see soft costs make up the majority of costs, while in Italian projects where project delivery is more efficient, soft costs are about 23%. So what's happening here is we're padding the budget, right, to avoid going over budget, which is not necessarily the problem in itself, but it's indicative of a larger problem that we have an inefficient project delivery regime, right? The fact that we need this much extra money to cover for inefficiency in our project delivery is a cause for concern. And of course, even when we pad the budget, we go over anyway. It's almost expected that projects in North America will go over budget from Toronto to LA, Montreal to Seattle. We've seen insane cost overruns because padding the budget, right, it means money is set aside, and money set aside is money spent. It incentivizes being lax with the budget, right? We have things we have to cover. Okay, fine, we'll spend the money. And it gets even worse when we think about how that cost estimate influences future projects, right? When we put a cost estimate out to procurement, the market usually comes in higher because, well, they know exactly how we cost our project. And because the next set of projects is based on the cost estimates of the previous projects, well, that's how we end up in this cycle of cost escalation. So how do we fix this, right? Low-cost countries on procurement, they focus on really transparent project delivery processes. They put in public benchmark costs and itemized contracts, like in Italy and Turkey, to make sure that not only is the public aware, but also the private contractors and public sector have symmetry. They also own the risk. They keep the risk in the public sector rather than giving it away to the private sector. Because if we price risk into procurement for the public sector to take, or for the private sector to take on, it results in a lot of extra overhead. And they also minimize contingencies. So, for example, in Italy and Turkey, they set like 7 to 12% contingency maximums that includes the cost of inflation. And what that allows is it sets an incentive for agencies to try to control the absolute cost of the project rather than staying within some kind of arbitrary budget. And let's move on to management. So we need to create strong agencies, right? We're overly dependent on consultants. We must build the expertise within agencies to expedite decision-making. And what that allows us to do is do more of our tasks in-house, right? We can reduce reliance on external consultants, and then the public sector knows what it wants. So when it goes to procurement, when it goes to market, we have a concrete design. We avoid all these change orders and the effects of not having a strong public sector. So some key takeaways from this presentation, high costs are not inevitable, right? Like they're not a result of external factors or force of nature. They're a result of deliberate choices that we make in planning and design, procurement costing, project management, stakeholder engagement, governance and politics, and the capacity of our construction sector. These are all things that are fixable. And lastly, I want to leave you with the goal of cost control is not to reduce scope, right? I'm not sitting here as a conservative trying to get you to cut your transit project or your transit project budgets, but it's saying that if we can deliver at lower cost, we can deliver better value and have more projects built. So say we could build for the cost of Paris line 15 at $190 million per kilometer, we could get 5 Ontario lines for the price of 1. That's the potential we have here, and that's what I leave you with today. Thank you very much. I welcome any questions.
Jedwin, great presentation, really interesting. I never thought that speaking English was a cause of increased capital costs, but that's I'll keep that in mind. Now I do have we got to wrap up, but I do want to ask a question. In your comparison of different potential factors in your literature review of the 1,000 systems, I noticed you looked at all sorts of different things. You did not, at least you didn't present one that compared different formats of P3 versus non-P3, bid design versus, and this sort of gets at something you mentioned at the end about bringing things back in. With the old design bid approach, it was all done internally. And the whole reason, but people perceived that being very inefficient and perceived that moving to P3s would externalize the risk factor and pass it on to the private sector. I've never believed that because I looked at the Croton line and other examples where the private sector just walked away from the risks that had gotten out of hand for them. And now I know Metrolinx has introduced a new collaborative approach to try to compensate for some of those, but the P3 approaches have increased dramatically those soft costs in terms of lawyers and so forth, and it's something that's always been used in England and in Canada. But it's not very clear to me because the US does not use P3 for transit projects, and yet their costs are even higher than Canada's. So any thoughts about that whole topic?
Yeah, absolutely. So this is something we covered in our study, but it's a whole other can of worms. And didn't want to touch in this presentation, but yes. So
I understand you have to be diplomatic, but still in general terms.
yeah, absolutely. So what the literature has found is that in general, low-cost projects abroad use design, bid, build. So that's the traditional procurement we talked about, right?
Yeah.
So the public sector takes it to a certain percent of design, then they contract out the construction. Well, what we see in US cases, right? Like those cases are high cost despite using quote unquote the correct procurement model because
Right.
the agencies lack a lot of expertise, right? And they hire consultants to kind of fill the gaps during the design phase. And they're really inefficient. They don't know, they don't know what the scope of the project is going to be. So what happens is even during the project execution phase, there's the same inefficiencies that we're seeing in Ontario, despite a difference in procurement model. And I can also speak, on the contrary, right? Like the lowest cost projects in Canada, like the Canada Line and the REM, were both extremely privatized in terms of risk, right?
Yeah.
Where we gave away all the risks to the private sector. And in fact, it's an interesting duality, right? Like the Canada Line, for example, was able to be so cheap because the contractors, SNC Lavalin, were basically, they had so much risk and they needed to keep the project under budget. And TransLink allowed them to make the decision to switch to Concur during the project delivery phase. So I guess it depends on who the decision makers are and are they also accountable for the risks. Because CDPQ, for example, delivering the REM in Montreal, they are the decision makers and they are accountable for the risk and they are able to deliver projects. So instead, like in Ontario, what we're seeing is we're kind of in this halfway point where like we want to give a lot of risks away to the private sector, but also like we want to manage them and want to oversight. So like we're in this strange middle ground that's not working. And it's the reason why, it gets back to the reason why I didn't want to talk about procurement is because it's more to do with risk. Like who is taking charge of the risk? Who is making decisions? And are those decisions, contributing to reducing the risk?
Yeah. Okay. We could have a discussion because
Yeah.
like I said, I don't believe the risk is ever really passed on to the private sector.
Right.
First of all, second of all, I also believe that part of it is the lack of transparency. So that makes it cheaper in the sense that
Yep.
you don't have to be accountable. You don't have to follow. I mean, the REM did not follow environmental rules. They had a very negative environmental assessment, and yet it didn't matter because they overrode. They were given the power to override any issues of that sort. But if you try to keep accountability and transparency, the soft costs are going to go up because you have to have more consultations. You're going to have to modify you can't just decide to do cut and cover like that. You're going to be forced into tunneling more and so forth. So it's still a very complicated issue. But
Yeah, absolutely. And I think like it's interesting because the literature sees transparency as almost a paramount in low cost countries, right? Like Italy and Turkey, for example, publish like costs for everyone to see. Anyone can go look at them. Even the government develops like benchmark costs for what the government is expected to pay. So that's a form of transparency. But then the other form of transparency is with like community engagement. I think that's more with like the process of community engagement. And when you look at like low cost countries like Spain, a lot of times they do community engagement, but they don't allow the community to kind of infringe their kind of perceived wants and desires on the project, and instead cost effectiveness is the priority. So it's an interesting contrast.
yeah, there are some comments in there. One. Okay, now a lot of the projects are underway. I mean, I guess the decisions have already been made, but do you think this kind of reflection of what that you've been involved in will have an impact on future projects? I don't know. Like the Hamilton one or the future Brampton one, I don't think have been decided in terms of well, maybe Hamilton's already been decided. I don't know, but I don't know. Just it's a good question. I don't think you could actually answer that. So
A great question. I can't answer, obviously, but
yeah,
I mean, I'm just a researcher, so I don't have much power. But
there And like we said, Michael points out that the three lower cost ones are full scale P3. So it goes both ways. It's not clear at all. Okay, there's some other good comments in there, but I think in the interest of time, yeah, there's issues are raised about cutting corners and about the lack of Canadian content and things of that sort. But anyway, fascinating discussion, and I will turn it over to Amber to wrap up the day. Thank you very much.
Okay, well, thank you very much. I hope you all enjoyed the presentations. It gives you an idea of the research. Oh, okay, I thought for a moment I was muted. Yeah, so it gives you an idea of what's going on in TAL. So there is, as I mentioned at the beginning of the event this morning, that all those projects are already done in partnership and sponsorship with industry partners, and the invitation is open to all. Whoever really is interested in partnering with TAL, you know how to reach us. You can send us an email, and we'll be happy to explore opportunities for working together. Um, so this brings day one to a close. There is still day two, and there's a little bit of transit tomorrow. So please make sure to come. There's a lot of exciting stuff. So CATS really is all about new technology, automation, connectivity, and one session will be focused on traffic AI, you know, how to manage traffic using AI. Another session on really behavioral impacts in the context of automation and connectivity. How do we expect actually people make decisions about mobility with respect to where they live and car ownership and mode choice and so on. All those behavioral aspects of travel will also be explored. And then the last session will be focused more on logistics and environmental impacts in the context of new mobility technologies. And we're also having a great keynote speech tomorrow by Roger Brown from the city of Toronto. Who's going to talk to us about congestion problems in Toronto and what they are trying to do to solve it. So again, one more time, on behalf of everyone at TAL, I would like to thank everyone who joined us today, and we hope to see you tomorrow as well. Okay. Thank you.